as members of the juries, of course, we have the two advisors of Cédric Collas, so Pierre-Yves Oudeyer from INRIA, Olivier Sigaud, a professor at Sorbonne University in Paris. We have Sebastian Risi, full professor at IT University of Copenhagen. Marc Bellemare, assistant professor Maile at Institut Québécois d'Intelligence Artificielle. We have Mrs. Laura Schulz, full professor at MIT. Felix Hill, research scientist at DeepMind, and Harm van Seijen, research scientist at Microsoft Research. So Cédric, you have 45 minutes to present your work, and then we will follow with the discussion and questions from members of the jury.
Great. Okay, thank you. Welcome to all of you, and thanks for coming today. So I will talk about the work I've been doing over the last 3 years, and I call it Towards Vygotskian Autotelic Agents. And it's about artificial agents that learn language from social interactions and then use it as a cognitive tool to organize their acquisition of skills. So yeah, in the first section, I'll introduce concepts and related work. And I show that existing methods for artificial skill learning can actually be seen as being inspired by the Piagetian tradition in psychology. And this will lead me to consider a complementary view inspired by the Vygotskian tradition. After that, I'll introduce two computational studies of what I call Vygotskian autotelic agents before I finally close the talk on some perspectives. So I'll start with concepts and related work. As a developmental AI researcher, I find inspiration in studies of human developments to design my artificial machines. And humans are amazing learners. In their first months of life, children learn many, many skills. And they learn to interact with objects, to crawl, to walk, to talk. And Jean Piaget, the founder of developmental psychology, he noted that this acquisition of skill is developmental in the sense that each skill that the infant develops holds both the fruit of the past and the seeds of the future. He also emphasized that children were autonomous. They were the leaders of their own development. So if we look at this child, there is no parent that went to hard code reward functions in its head. And they didn't even tell him which skill to learn next. So in the 1950s, psychologists went on to introduce the concept of intrinsic motivations to try to explain these seemingly suboptimal exploratory behaviors. And for them, it's a set of brain processes that push agents to explore the world for the sole purpose of experiencing novel situations. So of course, AI researchers quickly picked up on the idea and started to bake that inside their agents. One can mention knowledge-based intrinsic motivations, for example, which push agents to experience dissonance between their current representation of the world and their actual experience of it. So they will be pushed to experience novel or surprising things. And these ideas, they were recently baked into deep reinforcement learning algorithms, and they successfully organized the exploration in complex spaces. But today we'll talk about another kind of intrinsic motivations that we call competence-based, and that is oriented towards the practice of skills. So humans across their life, they represent their own goal, they pursue their own goal, they practice their own skills. And as they do so, they acquire an open-ended repertoire of skills along their life. And to define goal, I'll take a definition from Elliott and Fryer, and that's a goal is a cognitive representation of a future object that the organism is committed to approach or avoid. So in machine learning terms, we can see that as maybe a pair of a goal embedding and a reward function. And the agent is going to have its behavior conditioned on this goal embedding, so on the cognitive representation. And it's going to measure the progress towards the objective, so towards the future object, with the reward function. If you look at humans, we target actually a huge diversity of such goal representations. They span multiple modalities. They can be proprioceptive, visual, auditory, maybe linguistic, and also multiple levels of abstraction. They can be just moving the hand, or maybe going to the supermarket, or something maybe really abstract, like doing good research. And what we've seen so far, we can encapsulate it under the concept of autotelic learning. So autotelic comes from the Greek auto, which means self, and telos, which means the end or the goal. And for me, autotelic learning describe agents that are intrinsically motivated to learn to represent, generate, pursue, and master their own goals. So in practice, they observe the world through states or observations and act on it through actions. And if we were in a standard learning setting, we would have also goals and rewards coming from the exterior, from the definition of the task. But in autotelic agents, the agent has to generate them for themselves. And as they interact with the world in this way, they build repertoires of skills. So it's a set of goal representations and the associated goal-directed behaviors. And that's kind of our objective here, is to design those autotelic agents and to let them grow repertoires of skills. So here's how it's going to work. At the beginning of each learning episode, the agent observes the context and samples a goal representation. Then it can pursue the goal by generating appropriate actions in the world. It can measure its own performance by generating internal rewards. And once this is done, it can gather all the collected experience to update its internal models. So it can be goal representation, goal sampling function, goal reaching policy, and also the reward functions. And after that, it's ready for a new loop. It can learn for a new episode again. So in the last decade, developmental roboticists have come up with similar algorithms. They've called them intrinsically motivated goal exploration processes, or IMJEP. And they've designed synthetic and real robots able to target a variety of goals in many different settings. And they often focus on the use of learning progress to guide the selection of goals as a function of the agent's competence. But in those algorithms, they often assume the hand-coded goal representations and reward functions. And for these reasons, they are not totally autotelic just yet. These existing implementations, they rely on population-based algorithms. That's why we call them pop IMJAPs. And the idea is that for each goal, you're going to train one policy. It's good because it's simple to implement usually. It shows relatively good exploration. It's good to find core solutions to problem. It doesn't require differentiable functions. It's also really easy parallelizable. But it's not so good at fine-tuning policies. It's not so good at generalizing in the goal space or in the state space. And you can kind of fix some of those problems by maybe using deep neural networks as function approximators. But in that case, you're going to need many more samples. And if you want to fix these problems, you might want to use recent deep reinforcement learning methods that train just one policy to target many goals. They are better at fine-tuning. They generalize better in the goal space and in the state space. They have better sample efficiency. They do require differentiable functions. And they're not so good at exploration, but only in the standard implementations you can actually fix that. So that's what I started to do in my first project called JEPPG. And the idea was to combine the autotelic exploration of a pop IMJEP and the fine-tuning abilities of a reinforcement learning algorithm. So you work well to improve exploration. But I wanted to push further and to completely merge these two lines of work. So I designed this, what I call RL-IMJEP, which is basically an autotelic agent that is completely implemented with reinforcement learning techniques. And if you look at existing reinforcement learning, some of them actually perform similar mechanisms to autotelic agents. You have, for example, the goal conditional methods. What's good is that they target multiple goals, but they do receive these goals from the world, and they do assume encoded goal representations and reward functions. So they are not totally autotelic, although they target multiple goals. Curriculum variance, it's a bit better because they focus on how to sample goals as a function of the agent's competence. And this is where I made my second contribution in my thesis, which is Curious, the little robot here. And the idea was to target goals from multiple goal spaces inside a unique shared architecture to maximize the transfer of knowledge between the different types of goals. And I also used learning progress to guide the selection of goals as the agent learns. And so it can basically build its own curriculum as it goes. Moving on, there are also visual goal condition reinforcement learning algorithms that target visual goals, and they learn the representations by training an autoencoder and generates rewards by computing distances between the state and the goal within the latent space that they learn. And finally, there is the skill discovery methods that use information theoretic objectives to find a set of skills that maximally cover the state space and that are discriminable between each other. So those two last methods, they seem to learn goal spaces and learn reward functions. So they are autotelic agents in that sense. But so you need to find the good, no, sorry. So they do so by actually mixing some form of inductive biases, interactions with the physical world, and learning as well. And these mechanisms are actually really similar to the mechanisms of development listed by Piaget when talking about children. That's why I call them Piagetian Autotelic. But then the problem is that you need to find the right inductive biases so that they learn goal representations that are diverse, that are generalizable, that are interesting. But nothing ensures us really that they will learn goal representations that we as humans really care about. And so to think about that problem, I'll take us maybe a complementary view inspired by the Vygotskian tradition in psychology. And we'll show that maybe there is a missing ingredient in those agents. Okay, so let's do that. So you should recall this illustration that I showed before. And actually, I omitted a big piece of the puzzle. It's the fact that the world we live in is not only physical, but largely sociocultural. In the picture on the left, for example, there's the parents that organize a safe and interesting place for the child to explore. And more generally, our culture strongly shapes the way we represent goals, select goals, and things to which we attend. And this often occurs during dyadic interactions between a learner and a more knowledgeable others. So it can be a parent, a teacher, a coach, or a mentor, and in the end, we learn a lot from others. And this was basically put at the center of Vygotsky theory of human development. Humans develop cultural tools that they transmit to each other. And that helps, so once an individual makes some progress, it can quickly be shared with others, basically. So this includes physical tools to master the environment, but also psychological tools to master our own thoughts and behavior. And when I say tool, I mean something that mediates stimulus and response. So, or we can say also states and actions. And when the agent wants to gain control over its behavior, it can just decide to select the right artificial representations to mediate the two, to bias, to condition the behavior, its behavior. And Vygotsky thought that those psychological tools, they originate in interpersonal social relations. So he went on to define what he called the zone of proximal development, or ZPD. And this zone, it basically describes interactions between a more knowledgeable other and a learner, where the more knowledgeable other helps the learner achieve goals that are just beyond its current cognitive limits. And the goal of the learner in that situation is to internalize those social cognitive aids and turn them into psychological tools. So whenever a learner can do something with the help of the social partner someday, maybe tomorrow is going to be able to do it by himself, just by using the internalized psychological tools. So we can mention the use of language, writing, maybe the use of maps, mnemotechnic tricks, symbolic systems, and many others. But for now, we'll focus on the use of language, which is perhaps one of the most important. So we know that language is an efficient communication tool, but it's actually also a really powerful cognitive one. So Piaget first realized that infants, children talk to themselves aloud and kind of narrate their ongoing activities. And he thought that was the sign of their cognitive immaturity. But Vygotsky demonstrated that he was in fact witnessing the process of the internalization of social speech. Children, they use language to generate goals to themselves, to generate plans to solve them, or maybe to orient their own attention. And they do so just like the social partner would have done to them. So this social speech is internalized into egocentric speech, speech for oneself, and then further internalized into inner speech, the little voice in our heads. And since then, numerous studies have supported this view that language is a real Swiss Army knife for our cognition. It helps us memorize, represent abstract knowledge. It triggers perceptual and motor imageries in the brain. It can shape the way we attend to things that are culturally relevant or interesting. It can do many things. And so the two computational studies I'll show after that introduce two agents that use language as a cognitive tool. And they will do so in two different ways. 'Imagine' is going to use language to creatively imagine new goals. 'Imagine' is going to use language to creatively imagine new behaviors. 'Imagine' is going to use language to creatively imagine new behaviors. 'Imagine' is going to use language to creatively imagine new behaviors. 'Imagine' is going to use language to creatively imagine new goals. And Dexter is going to use language to guide the mental simulations of possible futures. So of course, I'm not the first one to think about using language in artificial systems. There were examples in the 70s already, but only recently could deep reinforcement learning take in a real sentence and use it as a goal. And so to do so, they learn the representations of those goals end-to-end with the policy, but they are still externally instructed and they still receive external rewards. And when you look at their motivations, they often mention the need to communicate with humans, but they rarely focus on the cognitive functions. So maybe the capacity for abstraction or the capacity for systematic generalization. And they almost never, or maybe never, actually internalize this language inside the agent to use it later. And if we take a Vygotskian view on the problem, we kind of understand that agents need to internalize the cultural goal representations, or the way to select goals, or the attentional biases. If they do so, they can start learning autonomously to target their own goals. They can also have a more structured exploration because it has the biases of our culture. And they can also start to use language as a cognitive tool. But before I start demonstrating these features, I'd like to say a few words about how to evaluate such autotelic systems. So ideally, we want to observe the emergence of an ever-growing repertoire of skills that the autotelic agent would gather by interacting with its physical-social world. And if we think about it, these autotelic agents, they are kind of generative models of goal-directed behaviors. And just like other generative models, for example, of images or language, they are kind of hard to evaluate. But there are a few things that we can probe. We can measure their exploration. We can measure their capacity to generalize to new goals, to transfer to downstream tasks, to be robust to non-stationarities in the environment or maybe distractors. And finally, it's often interesting to open the black box and to start looking at the learned representations of the agents. Maybe it's goal sampler, or maybe also looking at its developmental trajectories, so how the skills are learned and in which order. Okay, so now is the time to go over some results. First drink a bit. Okay, so I'll start with Imagine, which is a Vygotskian autotelic agent that's going to internalize social language to learn to represent goals and to imagine creative ones. So in reinforcement learning, usually what we do is that we have a hand-defined and fixed goal space, and we sample within the bounds of that goal space, but that's not really open-ended. So what people propose is to actually train a generative model of states and sample new states as potential targets, as potential goals. But this is limited because you kind of sample goals that are within the distribution of known effects. And if you want to push exploration further, maybe what you need to do is actually to generate out of distribution goals, to push your exploration outwards. And that's where language is going to come into play. Creativity is usually defined as novelty times appropriateness. And Chomsky thought that it was actually easy to be creative with language because when you assume some known grammar or known constructions, you can just unroll them to generate a creative sentence. It's going to be novel because it's going to be a totally new combination of words. And it's going to be appropriate because it's going to follow the grammar. So if you know what a cat and a bus are, you can actually compose those two concepts to form a new one, a cat bus. And if you're human, you can actually picture what it would look like in your mind. So as mentioned by Vygotsky and many others, language has this ability that it frees us from our immediate perception of the world. And it lets us represent the unseen, the unknown, something totally new. So maybe if autotelic agents could actually recombine the concept they know, so the goals they know, to generate new ones that are out of distribution, they could actually push their exploration outwards. So to test these ideas, we designed a continuous world where you can interact with objects. You have plants, you have furniture, you have animals, supplies, and you can procedurally generate them. So pick their color and their size. And so in that world, the agent can navigate to various places. It can grasp objects. It can grow objects by bringing them the right supplies. And in addition, we have a computational model of social interactions. So we have a simple social partner that observes the trajectories of the agents and describes it in a simple language, like you just grasped a red plant, for example. So now we're going to have two behavioral phases, kind of in Vygotskian spirit. The first one is going to be social internalization of language, and the second one, the use of language as a cognitive tool. So in the first one, the agent performs its goals and the social partner describes. The agent is going to store the alignments between the trajectories and the descriptions inside a memory. And if you look at this memory of description, you can see it as a non-parametric model of the goal space. So you can simply sample from that list to sample goals. And more importantly, you can also internalize the reward function. It's going to be just a classification system that learns to recognize a match between a scene, so a state, and a description of that scene. And once you've internalized those two modules, you can actually start training autonomously. You can start training without the social partner, because you can generate your own goals from the list. You can pursue them with your policy. You can assess your performance with the reward function, and then you can update your policy with some reinforcement learning algorithm. So once we've done that, we go to the second phase. We use language as a cognitive tool. And in practice, it means that we invent new goals by systematically recombining known sentences. So if we came across grass-bred tree and grass-bred cat, we can infer that cat and tree are actually things that can be exchanged. So when we see grow blue cats, we can replace cat by tree and invent a new goal, which is grow blue tree. And because we already internalized the reward function, we can actually directly train autonomously on this totally new goal. So before talking about the results, I'll say a word on the learning architectures. So first about the representations. We know that humans have object-based representations very early in their life, and we use object representations. So for each object, we encode the type of the object, the color, the size, the position, and whether it is grasped. And we're going to use these object representations in combination with an object-centered architecture. It's going to be based on an architecture called DeepSet, and the overall idea is that you can be invariant to the permutation of objects in your inputs. So you work on sets of objects instead of concatenation of objects. So this is what it looks like. It's a bit scary, but we'll go through it. So there is one version for the reward function on the right and one version for the policy on the left. Let's start with the reward function. So its role is to tell whether a scene and a description actually match. So they first encode the description into a latent goal representation, then they map it to some attentional vector. In this attentional vector, we're going to apply it equally independently to all objects. So maybe if the description is about growing a white cat, the attention should figure out that it should look at for the color of the object, the size of the object, and also the bit of the type encoding that corresponds to cat. So you apply the attention to all objects, and then you're going to encode the three objects into three latent codes. So 3 objects, 3 latent codes. They're going to be just one-dimensional, and you can think of everything I've just said so far as having independent, basically object-based, object-specific reward functions. So for each object, we see if the object satisfies the description. And once we have that, we can simply aggregate those 3 small rewards into scene global rewards for the scene. If any object is white, is a cat, and has grown, then the whole scene verifies the description. For the policy, it's a much more standard implementation. It's just a standard DeepSet. So each object is encoded into, this time, a high-dimensional vector, and then we aggregate those with a sum. So you can think of that as having object-specific policies that kind of compete within the sum to gain control over the agent. Okay, so now we have that, so we can internalize the reward function, and then we can use a reinforcement learning algorithm to train our policy with this architecture I just mentioned. And now, so this works perfectly, and now we're going to start goal imagination. And then 2 things can happen. It could be that the policy generalizes well, so it can readily reach imagined goals. Or it could be that the reward function also generalizes well and can readily recognize a match between a scene and a description, a new imagined description of that scene. So in practice, it's basically much more simple for the reward function to generalize than it is for the policy. it's easier to recognize when a new goal is reached than it is to actually achieve it. For example, it's easier to taste a cake and say that it's good than it is to actually bake the cake. But the good news is that because we have internalized this reward function, we can actually use our own learning signals to update the policy and to fine-tune the policy on these imagined goals. Okay, so we just went on to test that. So we designed a test set of instructions and we're gonna compare the generalization performance before and after goal imagination. So before goal imagination, the agent starts to grow animals. So it brings them water or food, and the social partner provides simple descriptions of these things happening. But the social partner never describes the same behavior for plants. So he never talks about growing plants, ever. But you can still ask the agents to test that, so to grow plants. So he has no clue, so he's just going to perform a sensible generalization and bring water or food with equal probability to the plants. But in that case, the plants, they only accept water, they don't really accept food. So this is kind of an overgeneralization of the policy. It doesn't work like that in the real world. But the policy cannot really know. But when you start goal imagination, you're going to actually start imagining performing those goals, and you're going to try to perform those goals. And at this point, the reward function is going to realize that it works much better with water. And so you can correct for this overgeneralization. You can use your reward function and its good generalization to fine-tune the policy. So you correct for that overgeneralization. And another effect that I think is interesting is that if you prevent the agent from training on some of those growing plants goals, so if maybe it can grow only, I don't know, trees and grass and roses, the simple fact of training to imagining to grow those plants is basically going to infer that other plants should behave the same too. And that's, I wasn't really expecting that actually, but this emerged in the network. Now imagination could have also another effect, and this time on exploration. So I said that when you start imagining out of distribution goals, they are totally new, so you're pushed to explore outwards. So that's the first effect. And the second effect is that in our case, we're internalizing the social goal representations. So they are quite biased in the end. They talk a lot about objects, about interacting with objects, growing objects, and so on. And so when you start imagining goals, you're going to have the same biases incorporated in your goal imagination. So you could imagine that you could grow plants and that's going to work. You can also imagine that you could grow furniture, for example. In that case, it's not going to work. But I would argue that it's still an interesting form of exploration because it's still biased to go in the world, interact with objects, trying new combinations and trying things. And so when goal imagination starts, on those dashed line here, you have the number of the counts of those interactions in the world that increases. So the agent starts really trying things in the world. And they increase over the baseline, which is the green one, where there is no goal imagination. So overall, goal imagination boosts exploration. So to recap, we've seen that Imagine internalizes social goal representations and turns these linguistic representations into psychological tools. And they use that to imagine goals, which boosts generalization and exploration. So from a technical point of view, this idea of internalizing reward functions and having this systematic goal imagination, so the combination of the two, is actually a pretty simple and general way to fine-tune the policy to make it better at generalizing. And we're not the only one to say that. There's a recent paper by Jacob Andreas, which proposes so combinations of sentences that is a bit similar, a bit more sophisticated maybe, and they use that as a way to do data augmentation on natural language processing tasks. And they also showed that just doing this on the training sets is actually a good way to improve generalization, and this even in tasks with natural language from humans. Now, from another point of view, so this goal imagination, it's actually pretty close to what children can be seen as doing when they do pretend play, when they start imagining their own problems when they play. And recently, developmental psychologists argued that this was actually a really adaptive thing to do, because when you do so, you kind of train to generate hypotheses and plans and that fits an arbitrary problem with an arbitrary set of constraints. So you learn to solve, to derive plans to solve really arbitrary problems. And that's probably something that is really adaptive to do for their future, to learn in a complex and changing world. And the idea is that you're going to learn to recognize the structure that is encapsulated within the problem or within the goal, to learn to find more efficient hypotheses that are valid with respect to the problems. And I think Imagine is also doing this kind of interesting things. Okay, so let's move on to the second study. It's Dexter. It's another Vygotskian Autotelic agent, and this time it's going to use language as a way to guide the mental simulations of possible future states. So before we used social linguistic representations in Imagine, and that gave it abstraction and creativity. But in fact, events often target really concrete goals on our day-to-day life. Pre-verbal infants, for example, they actually already show goal-directed behaviors even before language. And Spelke, in particular, maybe a bit Mendler, argued that they were relying on some innate or early developing representations of objects, space, numbers, actions, and social partners. And Spelke argues that it's language that then come after and maybe on top of those, and gives us this ability to represent abstract and cross-domain representations. The question is, how could we combine the concrete goals that pre-verbal infants target, but also the rest of us, with the more abstract linguistic goals that we develop later in our life, so when we get older? And we see that language is actually a good way to ground abstract goal representations into lower level representations, core representations. So in this study, we'll assume that we have such core knowledge representations of objects and their spatial relations. And we're going to use two special primitives, the close and the above relations. And these are in a set of about maybe 20 that Jim Mendler argued were the basis for concept formation in pre-verbal infants. So in practice, what does it mean? We have our agents in the right, this robot, it faces 3 blocks, and it's going to build its semantic representations by applying each of the 2 predicates, close and above, to every pair of blocks in the scene. So an example, here we have a configuration. All the blocks are close together, so we have all the bits of closed set to 1. And the red is above the 2 others, so we have 2 bits of above set to 1. So by doing so, we have a 9-dimensional binary configuration that represents the world. So this gives 2 to the power 9 possible configurations in that space. And in those, only 35s can be actually reached, but the agent doesn't know that, but it's kind of important. And this includes pyramids or stacks of 3 and so on. So Dexter, it's going to go through 3 different behavioral phases: a pre-verbal skill learning phase, a social internalization phase, and an instruction following phase. In the pre-verbal skill learning phase, it's going to store every configurations that it encounters. And it's going to sample goals from them, then target those and perform trajectories. And it's going to be able to compare those configurations it achieved to the desired one and generate its own rewards. And as it does so, it discovers new goals, it learns to reach them, it learns to master them, and this in an autonomous way, before language. Then comes social internalization. It's the equivalent of the one in Imagine. So the agent targets its own goals and receives simple descriptions of what's going on. But here we don't use those to learn a reward function. We use those to learn what I call a language condition goal generator. So it's a function, a generative model, that's going to sample a bunch of configurations like those that match a given linguistic input. So you can see that maybe as having a forward model at the episode level that mentally simulates possible future states that you could be reaching if you are following an instruction. Once you've done that, you can use language as a cognitive tool. So if someone asks you an instruction, you can sample compatible configurations, sample one from those and target it. And I say that it's a cognitive tool here because for 2 reasons. First, it gives abstraction. So we have an abstract language, abstract instruction, And we learn to ground it into lower level representations in a set of concrete representations. And second, it gives behavioral diversity, because for each instruction, you have several potential states that could match. And because you can select from those, you can actually gain some control over your own behavior and have a variety of behaviors. Okay, so let's see how this works. So before language, Dexter can discover all the configurations, the 35 of them, and learn to master them. But in practice, it doesn't work if you just let it sample goals at random uniformly. You have to give it some intrinsic motivations toward learning progress. So the 35 configurations, they're going to be grouped in 5 buckets, 5 groups of goals that have similar complexity. You can measure the success rates on each of those buckets as a function of time. So you see that the agent first learns about bucket 1, then bucket 2, and so on. And what it's actually doing, it's actually tracking its own competence, learning progress, and interest in each of those buckets. So the competence, you see that it tracks this relatively well. It starts focusing on goals that are easy. So it starts gaining a bit of competence. So learning progress increases, and thus interest increases as well. But as it starts to master them, the learning progress and thus the interest drop. So with this simple motivation towards learning progress, you're going to see emerge a developmental trajectory where the agent focuses on goals that are harder and harder as it learns to master them. Now comes social internalization. So I said we have to train a language condition goal generator, something that generates configurations from a linguistic inputs. And we're going to implement this with a conditional variational autoencoder, so generative model. So training time, we have the sentence, we encode it as a context vector. Then we have the encoder that encodes a configuration and a description of that configurations into a latent distribution. Then we sample from that distribution a latent code. And finally, we can decode the latent code and the context into a configuration, which hopefully is the same as the input one. So we learn basically to represent a diversity of configuration in that latent space. And we use standard VAE loss. So we have a cross entropy, which is just a reconstruction loss between the input and the output. And this term, which is acting as a regularization of this distribution towards the prior on the Z, which is the standard quotient. So at testing time, we can just use the decoder. We just sample the Z from the standard Gaussian. We have a context, and it's going to generate a configuration that matches the context. And if you sample several of those, you get several configurations. So when I say sentences here, I mean, we have really low-level sentences, like you put the red block below the green one. And we have also more abstract ones, like you made a construction or you got the green block on top. And the job of this goal generation, as we said, is to generate a diversity of configurations that all match the input sentence. And we can actually test that. And when we do, we achieve near perfect score on the training set of sentences. And it generalizes really well also to systematic recombinations of those sentences, so out of distribution. We also try to make it work to generate continuous targets for each of the blocks. So for a stack, you generate 3 positions on top of each other. But this way, we couldn't make it work. So maybe we can talk about that later. Okay, so now we can plug the two. We can ask the agent to follow instructions. So we have an instruction as input. We select a set of future states that could correspond. Then we pick one and we target it. When we do that, it works perfectly. It can follow all the instructions. We can also measure the behavioral diversity, so the number of possible final states that you could reach from any given instruction. And we find that for simple instructions, like you put the green block below the red one, it's about 16 different configurations that you can reach. And this is interesting because if you had a policy directly conditioned on the instruction, you probably would have just one behavior, one really simple behavior and no behavioral diversity at all. So these mental simulations of possible futures is actually offering this, this ability to switch between different behaviors. Not working anymore. Okay, it crashed. I will be back soon. Okay, sorry. Okay, so I said it's good to have the choice between several behaviors, because then you could switch strategies. So if you receive an instruction, you could sample the compatible configuration. And if you fail there, you can sample another one and switch strategy and try new behaviors. So let's recap. Dexter can learn to discover and master semantic configurations from its core knowledge representations of objects and spatial relations. It can internalize social language and turn it into a mental simulation system, which gives it capacity for abstraction and behavioral diversity. So in line with what Spelke says, we have this language that we can ground into more concrete, more core knowledge representations. In our case, an abstract sentence is nothing else than a set of corresponding configurations. But this is actually quite limiting, because the abstraction can only be a function of the properties that are already in the core knowledge. So if you don't encode, for example, the size of the object, then you can't build an abstraction of what it means to be small or large. But maybe what we can do is to actually learn to increase this core knowledge representation, these low-level representations, with predicates. So maybe we can learn classifiers that tell whether a door is open, whether the object is read, and so on. And if we can add those new predicates, then we can start building abstraction on top of those, kind of in a recursive way, I would say. Okay, so before the end, I'd like to open some perspectives for future work. So here's one that I find really exciting. It's the idea of giving a mental life to artificial agents. So here's a sketch of what it could look like. We would have a policy interacting with the world, nothing new. But then we would train captioners that learn to caption the external sensations, maybe trajectories, maybe images, and so on. So you get linguistic outputs of those captioners. And then you can feed that to content generators. Maybe you could have visual or motor imageries. Maybe you could generate language. And if the language is autoaggressive, then you kind of start to have inner speech in your agent. And all those contents that you generate, you can make them loop back to the policy or to the goal generation system. So you can generate content that actually influence the way you behave, the way you make decisions. And finally, those perceptual content that you generate, you can actually loop them back to the captioner to be captioned again and re-enter the linguistic loop. So I say that maybe we could have those inner loop, and from those could emerge some interesting behavior. Maybe we could have a visual system that learns to reproduce images and memories of past interactions that help you make decisions, or maybe mnemotechnic, I don't know, images that make you think of something and make the right decision. Okay, so the last point that I'd like to make is a connection with the concept of open-endedness. So human acquisition of skill is actually quite open-ended, just like natural evolution or cultural evolution. And in those divergent systems, it seems that the further you go, the more interesting, complex, and diverse it gets. And that's a bit what we want here. But the problem is that for people working on open-ended evolution, for example, they kind of have a hard time to actually agree on what it is that makes something open-ended and how to compare the quality of such systems. So it's not obvious to tell how to measure interestingness, complexity, or diversity between different skills, right? And so I'm not saying that I'm going to solve this, but my point maybe during the talk was that maybe we could piggyback on the capacity for open-endedness that humans have and that they demonstrate. For example, I learned a lot from others. I learned reinforcement learning a bit, and then I made some contributions pushing a bit further, and maybe someone can build on that and push this a bit further again. But my point is that we all make opportunities for each other, and we can all teach each other. And so maybe to get this open-ended behavior, artificial agents actually need to either have the same cultural evolution on their own, or maybe be integrated to ours. Okay, so that's the end. Before the end, I'd just like to say that all these results are the fruit of many collaborations. And so I'd like to thank all my co-authors that I listed here on the slide. On those two, yep. I'm also really grateful to my two amazing supervisors who have been, I'm sure will continue to be great, more knowledgeable authors to me. And I wish every PhD student could learn research in such good conditions with a good balance of, I don't know, freedom, trust, opportunities, and really good feedback. And finally, I'd like to thank the members of the jury for taking the time to read my manuscript and be here today. So thank you very much to all of you.